Hey y'all, this is our Unit 3, which is on functions and inverses. Our last lesson we talked about functions and relations. We'll get to the inverses a bit later. Today we're going to talk about a thing called function notation. Okay, so remember, a relation is a way to get from one set of data to another. A function is a relation where each input goes to exactly one output. So inputs and outputs are what we put into a function, what we get out of the function. And the collection of all inputs is called the domain. And the collection or the set of all the outputs is called the range. We showed relations with tables, mappings, graphs, and we didn't talk about equations or rules last times, but we will today, last times. The word rule is kind of the mathy word for equation. So if you hear the word rule, it means the equation, the process you're following. So remember that with a function, it's a specific type of relation where each input goes to exactly one output, and it can't go to more. If it goes to multiple outputs, it's not a function. So at some level, a function is just an idea of certainty. It's where, like, I know with certainty, if you give me one output, I can give you, no, if you give me one input, I can give you one output. I know with certainty for any input, there's just one output. So today we'll talk about functions as equations, which are aka as rules, and about this thing called function notation. So here's an equation that we're fairly familiar with. This is an equation in slope-intercept form, y equals mx plus b. It has a slope of 2, up 2, right 1, and a y-intercept of -1. Now this is a function, because I have certainty that if you give me an input, like say x equals -2, I can find the output. And the output, there's only one possibility. We plug in -2 for x, we get out -5 for y. It's the point -2, -5. Okay, we have certainty with one input that there's going to be just one output. Well, since we have that certainty, we can declare this is a function. And we declare that by using this odd-looking f of x. Now, this isn't f times x. It looks like f times x, but it's not. This is read as f of x. And the f just means we have a function. Okay, the f is telling us we have a function. F of x just means y. Really, it means your output. F of x is telling us what the output is. So I can take the equation y equals 2x minus 1 and write it as f of x equals 2x minus 1. F of x just means y. This might seem like, why? Like, what's the point of this? Well, it's going to make some things really simple and some things really clear. Like, remember how I just calculated -2, -5? I said, okay, x equals -2, so I'm doing y equals 2 times -2 minus 1, which is -4 minus 1, which is -5. So the input was -2, the output was -5. That's a lot of work to show a pretty simple idea. Input -2, output -5. X is -2, y is -5. With this function notation, I could say, what's f of -1? And this means I'm plugging -1 in for x. So this function notation, and notation just means a fancy way to write things. This function notation has me saying the x value is -1. I can now find the y value. If I have f of -1, I put a -1 in for this x right here. I can say f of -1 equals -3. And that's a point. This is now an input of -1, and the input is the x value, and the output is -3, and the output is the y value. Here's the point, -1, -3. Let's do another one. This is saying the input is 0. I'm plugging in a 0 for x. If I plug in a 0 for x, I get out -1 for y. So I have the point 0, -1. Input 0, output -1. I could do f of 1. Input is 1. So the input is 1. This also comes out to an output of 1. It's the point 1, 1. And I'll do f of 2. The input is 2. 2 times 2 minus 1 is 3. have the 0.23. This lets me see really quickly a collection of points with their inputs and their outputs. Input, output, input, output, input, output. And I know with certainty, because it's a function, each input only has one output. So I can graph these points. Here's the point -2, -5. Here's the point -1, -3, 0, -1, 1, 1, 2, 3. This forms a line with a slope of 2 and a y-intercept of -1. Really, I could take this table here and write it as a collection of inputs. Right? We had f of -2 equals -5, f of -1 equals -3, f of 0 was -1, f of 1 was 1, f of 2 was 3. See how this is like a table, right? Here's all the inputs, here's all the outputs, but I could draw it kind of like this. Here's the inputs, here's the outputs, but now it looks like a whole bunch of squiggles. But we're seeing again, we've talked about this before, the three main forms of a relation. There's equations, there's tables, and there's graphs. And this table and this graph and this equation are all showing, this equation right here, they're all showing the same relation, the same way to get from x to y. If we know what x is, we know we double it and subtract 1 to get y. This is our function. Okay, here's another one. F of x equals -2/3 x plus 5. I'm going to just plug in some numbers for x. Like, let's plug in -3. I picked -3 to be clear because this right here is a 3, and so I want to be multiplying by multiples of 3. 3, 6, 9, 0, -3, -6, etc. So this means I have -2/3, and for this x, I'm plugging in a -3. Now, -2/3 times -3 is +2, because the 3's cancel and the negatives cancel. So this becomes 2 plus 5, which is 7. So my input was -3, my output is 7. I'm going to do it for 0 also. If I plug in a 0 for x, I'll get out a 5. And I'll do it for 3. If I plug in a 3 for x, I'll get out a 3. I'll do one more. I don't want to do 5, because 5 will get me a fraction. I want to do 6. I'm plugging in multiples of 3 for x. See, I'm plugging in a 6 for x right now. So I'm doing -2/3 times 6 plus 5, which is -4 plus 5, which is +1. All of this right here, really everything on this whole page really is called function evaluation. Evaluate means find the value, like the numerical results. What do we get after we perform the calculations? Every time I plug something in for x, and I calculate the thing I get out for y, I'm doing evaluation. And I'm being smart and plugging in numbers that are going to be multiples of 3 to make the calculations easier. Like here I plugged in a -6. Well, -6 divided by -3 is +2. Don't know why I have two negatives here. -6 divided by -3 is +2, and 2 plus 5 is 7. No, it's +4, and 4 plus 5 is 9. Okay, functions, inputs, outputs. Now we can do a couple scenarios. Let's say that you're running 100 meters. No, you've already run 100 meters, and you're running at a rate of 6 meters per second right now. Well, the first question is this a function? Does this scenario form a function? What I ask myself is, do we have certainty? If you told me a time, can I tell you a distance? And I'm certain the distance I give you is correct and there's no other option. In this case, yes. Like if you've been running for 10 seconds, I can calculate exactly how far you've run and there's only one option. Since there's only one option, it means it's a function. One input goes to only one output. So the next question is, can we make a rule or an equation? Again, we can. This is just a distance equals rate times time problem, and remember, you have to also consider your starting position. Distance equals rate times time, but let's also worry about our starting position. So the rate, we know, is 6 feet per second, And I'll just use x to represent seconds. Number of seconds from start, or from now, I'll say. Our starting position we know is 100 meters. And let's just have y be our spot, our location, our distance. This equation models how far we've run in a given period of time. But instead of calling it y, I'm going to call it f of x to let everybody know this is a function. One input goes to only one output. And if I wanted to find how far have we gone in 10 seconds, I'd plug a 10 in for x. In 10 seconds, we've gone 160 meters. Input 10, output 160. Okay, every student at your high school has both an age and a height. I think that's a fact. Every student at your high school has both an age and a height. We can relate the set of ages to the set of heights. Like I can make a mapping over here, and it's a high school, so ages are like 13 through 19, I suppose. And heights could be anywhere from like 4 feet to 7 feet, I suppose, with, like 4'1" and 4'2" in between. Is this relation a function? Do we have certainty? If I said, hey, there's a 15-year-old, can you tell me with certainty how tall that 15-year-old is? No. Why? Because there's lots of 15-year-olds and they're all different heights. Some might be 4'2", some might be 7 feet. One input goes to more than one output, so it is not a function. Can the relation be expressed with a rule? You can have things that aren't functions but still have equations. We haven't seen it yet in our, algebra time together, but it's certainly a possibility. This one cannot. There's no equation where you tell me somebody's height and I run some calculations and I get their age. Or where you give me somebody's age and I run some calculations and get their height. That's not a possibility. Okay, so not everything has an equation with it, but it can still be expressed as a function, and not everything is a function. Sometimes one input has more than one output. So let's recap. A function is a scenario where we have certainty, okay, where everything is happening and we know for sure what's happening. A function rule is the equation that lets us move from inputs to outputs with calculations. Tables, graphs, and rules all express the same relation in different forms and their strengths and weaknesses with them. But probably most important out of all of this is f of x just means y. Don't make this more complicated than it is. F of x just means y. All right, we did it. See you next time.